All right, everyone, we're going to be looking at Lewis dot structures today in these notes. It's my first time really trying to use the stylus pen on a document. You know my writing is already messy to begin with, so I apologize if it's even worse than usual. So with Lewis dot structures, we're going to start using these instead of the Bohr model, as the Lewis dot structure is looking at only the valence electrons as opposed to all of the electrons that are surrounding that atom. So as you're going to see in a sec, these are a lot easier to work with than Bohr models. And they're also a lot more organized, and it shows bonds in a lot more simple way. So a couple of things that we need to make sure that we pay attention to while drawing these is that the elemental symbol obviously represents which nucleus we're going to be dealing with, and then the core electrons. So by drawing, in this case, lithium, we're dealing with the lithium nucleus as well as all of the core electrons. So you don't need to worry about including all of those. Each dot is representing a valence electron. So in a sec, you're going to see what that means. So each dot represents one valence electrons, and dots that are drawn in pairs are going to be shown that they're in the valence cloud. Okay, so when we're drawing pairs, that is going to be shown as a line when we actually get to the formation of the compound. Okay, so let's start actually looking at these instead of just talking about it. So if we're to draw lithium, I draw the symbol. That is representing both the nucleus as well as the core electrons. To show the valence electrons, if we look at our trusty periodic table, we see it's in our group 1 elements, and we all know that our group 1 elements have one valence electron. So I can show that by drawing just one dot. I move over to beryllium, which is in our group 2 elements. It has two valence electrons, so I can show that by drawing two dots. Simple. I jump across. Don't go into our transition metals yet because those are multivalent. They can have multiple charges, so we're not going to deal with those quite yet. If I jump across and I go to boron, our group 3, it has got three valence electrons, so 1 dot, 2 dot, 3 dot. Are we noticing a pattern? Go one more over. Carbon, 4 valence electrons. 1, 2, 3, and 4. Okay? Oh, I don't know why that disappeared. 4. If we go one over, nitrogen, 5. 1, 2, 3, 4, and 5. You see there that I drew one of them being the pair. It doesn't matter if the pair is on the top, the left, the right, or the bottom. You're still denoting that there's 5 valence electrons. I'm just showing now that they're starting to pair up. Oxygen, we've got nitrogen with 6, nitrogen with 5, oxygen is going to have 6. So 1, 2, 3, 4, 5, 6. Fluorine, following the pattern 7, 1, 2, 3, 4, 5, 6, 7. And then lastly, neon or noble gas, stable octet, 1, 2, 3, 4, 5, 6, 7, 8. So as you can see, even just with these ones, it's a lot more simple, straightforward, and organized in the Lewis structure versus the Bohr model. So let's go down and we're going to start looking at using the Lewis structures to show different compounds. So the first one that we're going to be looking at is we're going to be looking at our Lewis structures for ionic compounds. So we know that with ionic compounds, there is a transfer of electrons, and when there's a transfer of electrons, we're putting the square brackets around, showing a charge up in the top right hand corner. So let's start this off with, we've got sodium, And we've got chlorine that has sodium having 1 valence electron, chlorine having 7, as it's in our halogens. So we know we've got a metal, we've got a non-metal. So this is going to be losing valence electrons to form a positive ion, and chlorine is going to be gaining electrons to form a negative ion. We now have more protons than electrons with sodium, which makes it positive. We're going to have more electrons than protons in chlorine to make it negative. Okay, so how now can we show sodium chloride, our compound, in a Lewis structure format? So firstly, we have the transfer of this valence electron from sodium over to chlorine to make a stable octet. So since it's lost this valence electron, we can show that we have formed an ion, and we show its charge with the positive 1. Chlorine has gained 1 valence electron, so we can now show that this has a charge, and it is -1 because it's gained 1 electron. So if you're to show sodium chloride, an ionic compound, as a Lewis structure form, this is how you do it. You want to draw the brackets and charge. Now we're going to get into looking at covalent compounds. So these are where we're actually sharing electrons, so we can't show it in the same way as an ionic compound where we actually transfer it. So with this, we need to go through actually a couple of different rules. One, we always want to have a stable octet around all of the atoms. So we want to have each atom containing 8 valence electrons. Of course, we have some exceptions, being hydrogen as well as helium. Those are our only real exceptions. Okay. Some things that you want to do. Okay. You want to make sure that you're going to be putting down how many valence electrons you're starting with first. So let's look at question A here, and we can go through the steps. So the first thing you want to do is how many valence electrons are in the compound to begin with. So we've got 1 chlorine, so we have 4 valence electrons. In fluorine, we have 7 valence electrons, but we have 4 fluorines. So we're going to actually have 4 times 7 being 28. So we have 4 plus 28 to give us a total of 32 valence electrons to work with. The next thing you want to do after you've determined your number of valence electrons is you want to write down your central atom. With carbon, if you ever have a carbon in your structure or in your molecule, you want that to be in the middle. Okay, usually your middle is going to be the one that has the least number of atoms. So CF4, we have 1 carbon, so that's going to be in the middle. We're then going to connect that carbon to our 4 fluorines. Each line that I've drawn, so a line is equal to 2 electrons. So I've got 1, 2, 3, 4 lines to start with. So I've got 32 minus 8, which means I have 24 electrons left to work with. Is my carbon happy? Remember, I want to have a stable octet, so I can count 2, 4, 6, and 8. Good. So my carbon is happy, looking at that in terms of a stable octet. Now I want to start putting my remaining valence electrons around the fluorine. So I can just start placing them. 1, 2, 3, 4, 5, 6. Is this fluorine happy? 2, 4, 6, 8. It's good. I've placed 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, plus the other 6. So I've used 24. Stable octet, stable octet, stable octet, stable octet. So this molecule is good and happy. If I'm looking at question B, okay, I've got now a charge. That charge is telling me that I've lost an electron in this case because it is a positive polyatomic ion. So I've got nitrogen, that is giving me 5 valence electrons. I've got hydrogen giving me 1 valence electron, but I have 4 of them, which means I have 9 valence electrons to work with. I've lost 1 because of my positive charge, which means I'm working with 8. My central atom is going to be nitrogen because I have 1 nitrogen versus 4 hydrogens. And then I want to do my next step of creating a bond with each hydrogen around my central atom. So I've now got a stable happy hydrogen, stable happy hydrogen, stable happy hydrogen, and a stable happy hydrogen, right? Remember, hydrogen only needs 2 valence electrons, so these are all happy. I could then look at my nitrogen, 2, 4, 6, 8, as it's got 4 bonds containing 2 electrons each. Stable octet, my nitrogen is happy. The one thing that you have to make sure that you do is, since we are dealing with a molecule that has a charge, is I have to draw brackets and a plus. We're going to do one more example together, and then I'm going to leave the rest for you to do as some practice. So, all right, we're going to do our last example together. Sorry, I was going through on my own, and I made a little bit of a mistake, so we had to go back and refilm this. So we're going to finish off with our last example together, and then I'm going to leave everything else up to you to complete. But we've got our molecule containing H, C, and N. We know that our central atom, carbon, has got 4 valence electrons, hydrogen has 1 to offer, and nitrogen has 5. So we have a total of 10 valence electrons to work with. We know that we have carbon in our molecule, so that's going to be our central atom. So we're going to draw carbon, and we're going to bond our other 2 atoms of hydrogen and nitrogen to that. Hydrogen can contain a maximum of 2 valence electrons, so our hydrogen is happy. Right now, we know that we can have carbon have 2 more binding sites. So it's still not happy. It's got 2, 4 valence electrons, and right now nitrogen only has 2. So we're going to take our remaining valence electrons, that should be a 2. We're going to take our remaining valence electrons and we're going to work with 6 because we've used 1. We've got 2 bonds that contain a total of 4 electrons, so we have 6 left to work with. So we're going to put these remaining 6 around our nitrogen. So now nitrogen has got 2, 4, 6, 8, so it is happy, but nitrogen still only, carbon only still has 4, so it's not happy. So we're actually going to move these 2 valence electrons down here to create a double bond with carbon. So now carbon has got 2, 4, 6, getting there to that stable octet, and nitrogen has got 2, 4, 6, 8. So nitrogen's good, carbon is not. We can actually now move this pair of valence electrons into the bond with carbon to create a triple bond. Crazy, I know. And if we now look at it, we've got 2, 4, 6, 8 around our carbon, which is happy, and 2, 4, 6, 8 around our nitrogen.